Welcome back to Chapter 9, Part 3. We're going to be talking about enthalpy. Whenever you study thermodynamics, there are three important quantities that you're going to look at: enthalpy, entropy, and Gibbs free energy. In Chapter 9, we tackle enthalpy. It's important to know enthalpy is abbreviated with a capital H. Capital E stands for internal energy, so we need something different. So enthalpy is H. Enthalpy is defined as E plus PV, which is equal to heat flow at constant pressure. So that might sound like a complicated sentence at first, so let's break it down a little bit. We already know that heat will flow from an object that is hot or a region that is hot to a region that is cold, right? It's just relative temperature from where there is more heat to where there is less heat. But this will be impacted by conditions. This will be impacted by volume and pressure conditions. So if we look at something like the combustion of a mole of octane, right? We're burning up a mole of octane. If we have constant volume, right? And this is the example we're talking about over here. That's going to give off 4.45 times 10 to the third kilojoules of energy. So constant volume, meaning that we are in some sort of rigid container that can't expand or contract. Constant pressure, maybe now we have an open container so that the gases that are formed can expand. This is going to give off 5.48 times 10 to the third kilojoules. All right, so same reaction, same amounts, going to yield different energies. This may not seem like a lot, but if you're working on really large scale, that energy difference can be really significant. So it is important to recognize how conditions impact thermodynamics. Now, heat flow at constant volume, we're not going to be as interested in. Heat flow at constant volume is defined as delta E, really. So it's just the change in energy due only to heat flow. Because when we're thinking about chemistry, right, we know that delta E is Q plus W. Well, if we're holding a constant volume, that means our work, which is pressure times delta V, right? Pressure times the change in volume, that's the amount of work that's being done by a compression or an expansion. Well, that's going to equal 0, right? Because delta V, if we're at constant volume, is 0. So the change in energy, if there is no work being done, would be due simply to the heat. Now, doing chemical reactions in a closed container isn't always ideal. It's often very dangerous. And so more frequently, we're interested in constant pressure system. Now, this is essentially just a mathematical proof. But at the end, what we learn is that delta H is going to be our heat value at constant, not volume, at constant pressure. So let's run through it really quickly here. Enthalpy is defined as energy plus pressure times volume. We're never looking for just the overall enthalpy. We're looking at enthalpy changes. We're looking at what happens as a reaction progresses forward. So we're looking at delta H. And that's going to be the change in internal energy plus the change in pressure times volume. Now, where they go from here to here. If you remember, delta E equals Q plus W. Right? And we're specifically looking at pressure volume work, which is negative P delta V. So that has just been plugged in here for delta E. Now, since pressure is not changing, we can pull pressure out and it'll be P delta V. So we wind up saying that enthalpy is heat minus P delta V plus P delta V. So they cancel each other out. So at constant pressure, and that's important, enthalpy is your heat flow. So that allows us to quantify our heat flow for an open pressure, or for a constant pressure system. Okay. Now, things that are defined by enthalpy here, or some some words that you've probably been introduced to before, endothermic and exothermic. These apply specifically to these constant pressure situations where heat is being evolved from a system. That's going to give you a negative delta H, right? The system as it combusts is losing energy. And so we would say that that is exothermic. If delta H is positive, we're putting energy into a system, right? The system is absorbing that heat. This is endothermic, right? And that is all, that is all about the sign of delta H. So the sign has been important in this whole chapter and will continue to be. Now, before we get to enthalpy of chemical changes, let's look at changes in enthalpy for phase changes. So let's review a little bit of vocabulary here. As we go from solid to liquid to gas, we know most of this terminology, I know, but I want to review because I know some of them aren't as common and some of them are just different for chemistry. For instance, starting off, we know that when a solid changes into a liquid, we say that that is melting. You are going to see that referred to as fusion. As a liquid changes into a gas, right? This is vaporization or evaporation. And if a solid goes straight to a gas, this is sublimation. Right? All three of these arrows are going from a lower energy state to a higher energy state. All right, so going from solid to liquid, going from liquid to gas, this all requires us to put energy. It requires the system to absorb energy. So all of our blue arrows here are endothermic, right? They would be a positive delta H. Switch up our pen color here. Let's do purple. I guess for those of us with any sort of color issues, maybe red is more obviously different. All right. Now, if we're going from these higher energy phases to a lower energy phase, all right, gas to a liquid is condensation. Liquid to solid is, of course, freezing. And gas to solid is called deposition. You should know all of these terms. Your red arrows are going from higher energy to lower energy. So when a gas condenses to a liquid or a liquid condenses to a solid or freezes, this is going to be exothermic. It is going to give off that extra energy. And you're going to have a negative delta H. These phase changes sometimes are written, here we go, as, for instance, delta H of vaporization. All right, you'll see a little subscript to indicate, or delta H of fusion. You see in this chart here, they don't use that, but you have some standard enthalpies for fusion, freezing, vaporization, and condensation of water. Something that's important to note here is that the amount of energy it takes to go from solid to liquid is the same amount of energy that it is going to give off when that liquid freezes back into a solid. So what you notice here is delta H of, and let's not do vaporization there. Delta H of fusion, right? So the melting is equal but opposite in sign to delta H freezing, right? If a mole of water requires 6,009.5 kilojoules to melt, when it freezes, that same quantity of water will give off 6,009.5 kilojoules, or I'm sorry, joules of energy. You see the same when you compare vaporization and condensation. The vaporization is endothermic, the condensation is exothermic, equal and opposite. Shouldn't be surprising that vaporization and condensation are significantly larger than fusion and freezing. When we're going between solid and liquid, we're still in condensed phases. There are still a lot of intermolecular forces. But to move between a liquid and a gas, right, you're having to break all of those intermolecular forces. There's a much bigger energy difference. Something that is also important to note here, and we're going to learn more about it when we talk about Hess's law, but delta H of, let's pick sublimation, going from solid to gas, that's actually going to equal delta H of fusion plus delta H of evaporation. Let's just put evap there, right? The amount of energy to get from solid to gas should be the same whether you go through a liquid or you go straight to the gas. So that's something to note. We will see that pop up again a little bit later. Standard molar enthalpy is what you're seeing over here on this slide, is at a specific temperature and pressure, and it's just, you want to hold as many things constant when you tabulate data like this so that you can compare different substances. Well, I guess not constant temperature. Obviously, the temperature is going to be different here, but you're looking at 1 mole of substance, and you're looking at constant pressure, and probably looking at 1 atmosphere. We're looking at a specific constant pressure. This allows us to make certain calculations because we can look up this tabulated data based on a mole of substance. We can apply that to different amounts of that substance. So if we're going to calculate the enthalpy change of 245 grams of ice, there's a couple of things that we want to know. We want to go from grams of that solid water to joules. So we need some relationships here. We know that, and if we're looking at melts, we're looking at fusion. We know that there's 6,009.5 joules chemically related to 1 mole of water, right? Because that's the molar enthalpy. That's that delta H of fusion. We know that grams and moles are related because there are 18 grams of water in 1 mole. And this just becomes dimensional analysis at this point, right? So I've got all that data there. I'm going to start with my given like I always do. I want to convert 245 grams of water to energy. So I'm going to divide by my molar mass. And I want moles of water to go away so I can get joules. So I am going to use this relationship here. I know there's 6,009.5 joules needed for every 1 mole of water that is going to be melting. So moles of water cancel out, grams of water cancel out, and I'll just be left with joules. And at the end of the day, that equals 81,795.97. If I want to pay attention to sig figs, which you know I do, I'm going to round that to 81,800 joules. And that's how much energy it would take to melt 245 grams of ice. If we continue on, that's one kind of calculation that we can make using those delta H's of phase change. Right? You will be able to find more practice in your homework and some practice problems that I will put up on eCampus. This takes us nicely into what a phase change diagram looks like. It's important when you look at a phase change diagram, right, that you notice some key features. For instance, this specific one is water that we're seeing on the slide, but all phase change diagrams or delta H phase changes look similar. You have an increase, a flat, an increase, and a flat. What's important to know here is that temperature is constant during a phase change. All right, so if we look at water at -50, right, that's going to be solid ice. is you start to apply heat. That's what's happening along this x-axis. The temperature of that ice is going to go up. Once you get to 0 degrees, the temperature stops going up. All of the energy now is used to convert that solid to a liquid. And until all of the water is liquid, that energy is not going, or that temperature is not going to increase. Right here, where all of our solid ice has been converted to liquid water, the temperature will start to rise again. Once the temperature of your liquid gets to its boiling point, right, 100 degrees for water, then it's going to flatten off again, right? All of the energy in this flat area is being used to convert from liquid to gas. All of that energy is being used to break those intermolecular forces, all those hydrogen bonds. It's not surprising to see that this is so much longer. It takes a lot more energy to go from liquid to gas as compared to solid to liquid. You're really breaking through all of those intermolecular forces. Once everything is converted to steam, once all of your molecules of water are in the gas phase, then the temperature can increase again. This is one of the reasons why a water bath is so useful in chemistry. Your hot plate can be finicky at times. It can be hard to control. It can be hard to get to a specific heat and stay there and not go above it. So if you perform a reaction in a hot water bath, well, you know that as long as you have liquid water, that temperature is staying at 100, right? It's not going to go any higher than 100 no matter what you do with your hot plate. All right. The next few slides I'm going to skip over. They refer back to that insight at the beginning. And I'm going to go straight into a little bit of a discussion of heat of reactions. So we've looked at heats of phase changes. Heats of reaction, or enthalpies of reaction, right, delta H of a reaction, are going to refer to the energy change, the heat flow occurring in a chemical reaction. Right? When we talk about chemical reactions and heat flow, something that's important to recognize, we're looking at the changes in the energy when the bonds break and when the bonds form. What you should highlight here is bond forming is always exothermic, right? A bond isn't going to form unless it gives you a lower energy state and releases energy. So, therefore, when you make a bond, you're always going to release some energy. Breaking a bond, on the flip, always is endothermic. It will always take some energy. You have to put energy in for a bond to break. Whether or not a reaction is endo or exothermic depends on the energy of the bonds breaking in the starting materials and the energy of the bonds forming in the products. A thermochemical equation, so we've looked at balanced chemical equations already, but now we are looking at a balanced thermochemical equation. That's going to require one additional piece of information, and that is your enthalpy. Let's highlight that too. That's going to be your enthalpy of the reaction. If you look at this whole thing, this is a balanced thermochemical equation. You have your starting materials, your products, all of the atoms are balanced, all the elements are balanced, and the delta H. All together, that makes a thermochemical equation. And it's important that you recognize that it's balanced, because what this is telling you is that when 1 mole of methane reacts with 2 moles of oxygen and makes 1 mole of CO2 and 2 moles of liquid water, this is the exact amount of energy that is released. Now, I know it's released because it's negative, right? So this is an exothermic reaction. If we make any changes, then it has to remain balanced. So for instance, if I wanted to look at how much energy 2 moles of methane would release when reacted with, I already messed up, 4 moles of oxygen, right? We know that we would have to keep this balanced, so we would make 2 moles of CO2 and 4 moles of water, right? To keep everything balanced, everything had to be multiplied by 2. So delta H is no different. The end result there, right, would be a delta H of negative 1780.8 kilojoules. Right, so it is affected, whatever you do to the reaction, you also have to do to delta H. If you were to look at the reverse, right, and let's see, I'm not sure what's happening on the slides over here. Hopefully when you pull them up yourself, you're not getting these weird little, I don't know what that is. Before we move on, let's see. I also wanted to talk about if you flip it. So let me blow this up just a little bit for us. If you were to look at the reverse reaction of carbon dioxide, if it could somehow react with 2 moles of water to give us a mole of methane and 2 moles of oxygen, delta H would be the same, but it would be opposite, right? If we just flip the reaction, this is going to require us to put in 890.4 kilojoules per mole of methane and CO2, right? These manipulations are going to be important in part 4 video, right? Whatever you do to the reaction, you have to take that into account with delta H. Right? If you multiply, then delta H needs to be multiplied. If you divide, delta H would need to be divided. If you flip it, the sign needs to be flipped. Now, sometimes you're going to see delta H for specific reactions, and instead of RXN, they may have something that's more appropriate, like delta H of combustion, if you're looking at combustion reactions, NEUT for neutralization reactions. One that we're going to use quite a bit is delta HF, which is heat of formation. Heat of formation is the change for making 1 mole of any substance from the elements. Now, a couple of things we want to note here. Something that hopefully you see is this little degree sign next to the delta HF. That means that we are talking about standard state. So carbon is a solid at standard conditions. Oxygen is a gas at standard conditions. So here we're talking about the formation of carbon monoxide from the elements in their standard states. It's also important to know, right, that we are always talking about 1 mole of a substance. So it should be balanced, but this is a time where you might see fractions in your balanced equation, because what's more important is that this is a 1 right here. All right, so delta H of elements in their standard state, right, is going to be something that can be calculated for any substance. There's tables and tables of data of heats of formation that are going to be useful for us when we get into some Hess's law calculations. Yeah, standard state. So we should make notes of that really quickly before we move on. It's standard state here. It's not standard temp and pressure. You'll notice it's 25 degrees C and 1 atmosphere. You're not required to memorize that.